The oceans are deep, dark, and mysterious. And as the scourge of climate change gathers momentum, we as humans are racing to understand the movement and often the rage of flowing water currents, albeit to harness them as sources of non-conventional energy. But the challenges are far too many. The major one being what exactly is happening in the womb of oceanic depths. So, far and wide in our oceans, sensors are silently collecting data. That too has its own challenges, as is obvious from my conversation with Jordan Bouchard, Postdoctoral Fellow at the Water and Energy Research Laboratory, Department of Mechanical and Industrial Engineering at the University of Toronto. Okay, so tell me a little bit about the project.
And so the project is dealing with trying to capture energy from ocean currents. And the reason why we want to do that is that we have sensors such as salinity sensors, light sensors, and wave sensors, and they're always distributed throughout the ocean. And what's really hard is to get these sensors for the power, because if we want to download data from the sensors or recharge the batteries, we'd actually have to hire a ship to go out and get personnel to bring the sensors back up, change the batteries, and download the data. With this option, we're trying to create an energy source that will stay in the ocean with the sensors and continuously recharge the batteries, so that we don't have to continually sending out a research ship to go and get the sensors and bring them back and recharge them and download the data.
So so it's at a nascent stage, or it's being developed and it's already in operation? What stage?
No, it is nascent. It's pre-commercialization, I would say, or pre-development. Right now, we're still trying to prove it as a concept. The way we started off was the idea. What happens now is with the most common way is that they'll have a buoy anchored to the ocean bed, and then on the buoy will be an array of solar panels. The solar panels will charge batteries, and then that will send a wire down to wherever the sensors are below the surface of the water. That will keep it powered. However, having a battery pack that has to be very large is expensive, because the sun doesn't shine every day. It has to power it overnight. And another way you could do it would be to have, say, using the ocean waves at the very surface. But there's not a lot of energy in ocean waves, and again, you still have to have a large battery pack to make sure that if on the days you don't have enough wave action, you're generating enough energy to power the sensors, because you don't want to have gaps in your data when you're trying to do analysis in terms of weather tracking or hurricane tracking. So what we started was that, well, what if we move below the surface? And below the surface is, depending on I don't exactly know how it works or how they're generated from, but there are currents, and the water will move slowly, generally in one direction at a constant velocity. And they know where these currents go, or generally are, throughout the oceans. And so the idea was that if we make a large turbine and have it spin very slowly, powered by these currents, is that enough energy to capture and to power these sensors?
So what level, how many feet below the surface would this be, where the currents are generated?
The currents would be generated, I think, anywhere between 50 and 100 meters below the water surface.
So even going down there, and it's just sensors that you're using, or is there anything else that you're using just to gauge the movements and the strength of the current?
They will measure that with a different type of sensor.
Yes.
And so what you could think of is that there'll be a buoy on the surface of the water, and then that will be on a steel cable anchored to the ocean floor. And then along that ocean floor, they'll have sensors attached: temperature sensors, salinity sensors, oxygen content sensors, and then our turbine would also be anchored to that. And so the turbine would send out a power cable and go to all the different sensors. and it'll be low enough so that as it'll be in the ocean current stream, and the ocean current will spin the propeller, which will generate the electricity that is needed, and then on board the turbine will be a small battery pack to recharge.
So to my mind comes the fact that you'll be going deep into the ocean floor. It's very expensive. The first is even if it commercializes itself, the companies that will pick it up, there's a lot of expenditure. So do you think it's a feasible thing to go in for? I know it's a renewable project.
It's a renewable project. It's feasible because the amount of money it takes to operate one of these ships easily pays for the cost of the turbine. So again, it's hard to put exact numbers to it, but say to operate a research ship could be on the order of $1 million a day. A day, right? And so they don't run the research ships very often, and usually to run it, it's multiple teams and multiple groups around there in order to make it cost effective. Whereas this turbine might cost on the order of $50,000 maybe to $100,000, and you just pay for it once and you leave it out there.
So that's your research, that's at the research level, but when it comes to the commercialization level, the turbine will have to be a mighty one because the ocean currents can be pretty rough. And then how many households or how big of a city, let's say if you were to hypothetically do Toronto, would one of those turbines be able to produce the electricity for?
So that's a different scale of turbines. So you might be thinking about the turbines or the wave or the tidal generators that they're called. The tidal generators in the Bay of Fundy are one example, and you're right, the amount of energy that's in the tidal zone is immense, and I think that those turbines got destroyed when they pulled them up again. Ours only generates 1 to 2 watts, right? And so a household will run 2,000 to 3,000 watts. Well, what a household could consume, or 2,000 to 3,000 kilowatt hours. Now, we don't have to really worry about being mechanically strong, is because we're below that level of the wave interactions, and all that turbulence that's happening on the surface won't affect our turbine.
So basically, right now you're just concerned about the feasibility of having a project like this. The project is all about the feasibility of generating current or electricity from ocean currents.
Yeah.
And later on, how they adapt it to a bigger volume is a different theory, or is a different.
Yeah, and I don't know if you'd be able to scale it up and to do it on a household level, because the amount of energy that's in there is just too small.
So what would be the purpose of your research? What are you aiming to achieve with it?
The research, we're trying to replace having to have a research vessel hired out to go out and maintain the network of sensors. So all across the world, there's hundreds of thousands of sensors deployed in the ocean at all times, and we'll say they're the temperature sensors. They're monitoring how much the water level is changing, and they use those to help predict weather systems. Okay, and that network of systems has to be maintained. You know, a ship has to go and see the sensors once or twice a year, or once every 2 years, and that is the opportunity that we're trying to exploit. Is that can we have this turbine to replace having to send people out to monitor these sensors, and can we just use the turbine and save on the cost of having to send somebody out?
So what have your research findings so far told you in terms of the research that you're doing, change of current or the...
Yeah, so we found that the turbine is feasible, right? In terms of as a first pass, so that we have a prototype and we tested it at currents that we would typically see. The power generated was at the level that we hoped for, and now what we're going on to our next stage is that we're trying to optimize the design. For one example is where we're concerned about trying to what we call as the cut-in speed, is that the cut-in speed is the minimum current velocity that will cause the turbine to spin. right now it's a little bit high, and we're trying to get that lower. So the lower that we can get the cut-in speed, the longer the turbine will generate electricity.
And how's your research funding going on? I mean, who funds your research? What are the bottlenecks there?
Yeah, so we're partnered with the CSIRO. I think it's the Commonwealth Industrial Organization of Scientific Research,
okay.
And that's based out of Australia. They funded the first stage of this project, and I believe that they're helping fund the second stage of the project. What we do is we apply for generic grants through the National Research Council of Canada, and they provide some of our funding as well. One of the problems that we face is that as we go from an idea or a concept, and as we're going and moving on to a real product to be put into the market, then the funding gets a little bit more difficult to acquire. The government is, most of their funding is more for theoretical research, and as we move into a commercialized product, then we have to start to engage the private sector. So one of the next stages that I'll be working on is trying to find a company that wants to partner with us to help develop this into make a larger scale prototype and deploy it out into the ocean and do field trials with it.
So what's the end aim of the project? It's just to monitor the oceans? It's nothing to do with creating renewable energy, or is it both?
It's creating renewable energy, but it's creating a really small scale renewable energy.
And just to monitor the changing currents or the oceans. And this will be a huge, oceans are really vast. They are 90% of 70, 80, 90% of the landmass.
Yeah, I believe it's around that 70% of the ocean of the surface area is ocean, and by doing this, we should be able to actually monitor it more, right? It's right now we're limited by the cost of having to get these sensors out and maintain them. If we can reduce the cost of maintaining these sensors, then we can potentially deploy more. And with better data, we could feed that into our climate models, which are mostly for predicting the weather, right? And so if we can predict the weather better, that helps a lot.
Yeah.
That's where the ocean research goes.
Just a quick thought comes in my mind. How much of the ocean, I mean, it's all common property. You know that there are there's a continental shelf and all that. So do you run into any kind of geopolitical issues with this? Because, you know, a country could say, hey, you can't do this here. This is not your continental shelf. It's like fishing industry. They have a huge issue with that as well. Do you face that?
We haven't had any of the issues yet. I would imagine, and yes, so we would. I would imagine that we would have to partner with whoever owns the sensors and the buoys, right? We wouldn't be able to attach it to anybody's, and we would have to approach them and say, hey, would you like to buy this device to power your sensors? And then they would have to agree or not.
So is it individual countries?
We'd have to do it, it's individual countries through their research organizations.
What are the other bottlenecks that you face, or what are the successes that you've had? Both, I mean, successes and bottlenecks, in fact.
One of the main bottleneck that we had was manufacturing it in a way that was economical, right? So this is all custom equipment. So some of the equipment is we use 3D printers to make the turbine blades and the nacelle of the turbine, and then we use components that you can find off the shelf in a hardware store. But 3D printers can only print 6 inches by 6 inches by 8 inches,
right.
And our turbine is so we'll stay in inches here. It's about 45 inches long, and and probably has a blade sweep that's also about 30 inches long, tall. So we had to print the pieces in smaller parts, glue them together, sand them to make sure there was no cracks. All of our equipment had to be leak tested to make sure that it could withstand and not have any water flow into the components, because there was a generator inside and there were batteries, and so we had to keep it dry. But we managed to solve some of those problems. Another big hurdle is that it's always that we're doing it for the first time, and so we've had the student that worked on this. He had to learn everything from from the ground up and build it by himself. And since it was during COVID, there was very little help that he could actually ask for. So it was very impressive that he got it from a theoretical point and actually made a prototype within a 2-year time during COVID, and then got it tested. It was very impressive for a student to do that.
Do you see any company picking this technology up? Why would a company invest in something that's a government domain, like keeping track of currents, and that's
because the government is interested in the data, but they do not make the equipment, and so a company is interested because they could sell the equipment to the government.
To the government,
yeah.
Yes.
Or they maintain the sensors arrays for the government as a contract.
And so, do you see the role of satellites there, or is it just independent of everything? Because climate is an issue between the sky and the oceans and the earth. It's a vast thing. Mm-hmm. Do you see any? But of course, it's just a beginning. But do you see any it expanding into that into
the satellites?
Because there is a satellite system that monitors climate, but not the. Climate.
They have to link together. As you're right, they have to link together, and so the data from both sources would link together. We use a satellite array to communicate with the sensors. So they would communicate their data to a satellite, and then the satellite would communicate that data back to the ground home base of operations.
And is anybody else involved in this, or you're the only institution? I mean, University of Toronto is huge. And
we're the only ones doing this right now. It's a new technology, and we're trying to develop and commercialize it. Other groups are working on the same problem, but they're taking different approaches, right? So the same base problem is, how can you provide power to these sensors instead of batteries?
So how much do you spend on the batteries right now?
The cost of the batteries is going out to change them, or to go out to charge them.
Because you have to hire all those.
You have to hire a ship. You have to hire people, and you have to go out.
And how much of the ocean have you been able to cover so far? I mean, where is this, or not at all? I mean,
I don't know. So in terms of how many devices we've installed, none. We're still trying to test and validate that it can work, because the cost of it might be on the order of $50,000. So we have to have enough data to convince a company that this would be a good idea to buy and to build.
But nobody else has put their sensors in the ocean as yet. But there
are lots currently.
There are lots currently. So you would be looking at what specifically? What areas of the ocean? Is it
because we're partnered with
Australia,
with the Australian government, we'd be working in the Indian Ocean.
And that's a huge, and that's a lot of the currents go south to north, I guess.
They can go south to north, north to or east to west.
East to west.
There, I can't remember what that current is called, but it was in the south. It was in the Indian Ocean that we modeled the performance off of it as a starting point.
So you hope to have a pre-warning system, tsunami system, because would you be able to, after all these sensors are involved, let's say there's a huge tsunami brewing in the ocean belly, would you be able to detect it, let's say, a day or 2 days ahead to save lives?
Depending on where the earthquake happens and the distance it is to land, the sensors that are there right now could potentially be powered by our system. Right? So, and if it's cheaper to maintain it, then there's potential to put out more early warning systems for things like tsunamis or earthquakes.
So I look at it that the big companies may be involved in this later on. You haven't approached anyone, or no one?
We haven't approached anymore. It's always a little bit difficult because the companies want something that proven to work, right? Like we have to. It's managing the risk, right? And we don't want to give up something that's not quite ready yet as well. Like we don't want it to be. I guess we still want to be involved in it. Right?
I know.
And that's the idea. Like you want to it's like almost like your child, and you kind of want to keep it close, and you don't want to let it go yet.
Absolutely. So UFT is partnering with anybody else. Of course, you have the Australian government.
Yeah. So it's mostly led up by our research group. So we're our research group is called the Water and Energy Research Laboratory, and it's up to our principal investigator, Amy Bilton, so she will contact companies and lead it and make the connection, and if required, then we'll involve the University of Toronto with it. And that's usually involved in terms of when we get involved with patenting and licensing or any type of intellectual property, then the University of Toronto gets involved to make sure that the proper contracts are in place.